Again, we have Professor Kwek Leong Chuan, and the talk is about eco-friendly chip-based quantum and classical neural networks.
Right. At some stage, I'll digress a little bit, but let me start off by thanking the organizer for the invitation to give a talk. And let me first show you the Frontier supercomputer, which is supposed to be one of the most advanced supercomputer we have now. It has an energy consumption. I took it from Yasser Omer, who gave a series of talks, who gave a talk at the QEI consortium recently. And the energy consumption is 1.19 times 10 to the power 5 electron volt per bit of operation. Now, very often you need such figure to compare the advantage between a classical computer, or so-called classical supercomputer, and a quantum computer. And so such figures becomes essential as a sort of benchmark. Now, this is the talk by a paper written by Alexia, who's the organizer of this whole operation. And she mentioned in this particular paper that there is at the moment, 10% of the world ICT energy consumption is used for computing. But it is expected that by 2030, which is in about 5 to 7 years' time, we will reach 13%. And this is a report by the IEAE. So Alexia have gone on to look at the energetics of a single qubit gate. I'll just not talk too much about that. You can ask her. She's here in the audience. And also there are energetics of a single quantum gate that's been done experimentally and also theoretically. So this is a paper by, I can't even see the screen, sorry. Myself, maybe I look at this, by a couple of people, experimental realization. I thought that was by Yasser Omer, but it's not. So there are quite a few papers. I'll skip some of this. And this was a slide that was shown by Yasser recently, where he looked at the implementation of Toffoli gate for adder, and then he looked at the energy consumption. And it turns out that the half adder or operation that he did was not with a ion trap or supercomputing superconducting qubit is not as good. So essentially, we are not there yet. So let me go into another platform that we should also harness for computing. And this platform is what's called integrated photonics. Now, integrated photonics has certain properties. And as you can see, they are pretty transparent, material-wise, very stable, and with typically very low consumption of power. And one has to consider, in fact, a hybrid integrated quantum photonic circuit, and that was a paper done by Val Zwiller, and published in Nature Photonics. I'll skip some of this because it's just an overview of everything. So the history of integrated photonics, I'll skip. So why integrated photonic chips? And the reason is because electrons are really small, just like, and so are photons. Photons are perhaps even smaller. And electricity moves really, really fast, but light moves faster. And so it's just not the speed of light that is exciting, but also its capacity. Electrons moving through a copper wire carry a limited amount of data and over short distances. And optics, on the other hand, can go much further. So this is some of the advantages of changing to photonics. Now, there is something about photonics that is not so good. Photons do not talk to each other. They don't interact. And one way to couple that is to consider nonlinear device. And so nonlinear device produce what's called polaritons. And so that's an area that is being planned for, in fact, in Singapore itself. Our first, this historically, how we started to go into chip-based chip-based photonics, integrated photonic chips. And historically, we started off with QKD. And in fact, the first paper, you can get it from the, this review paper, but the first paper was actually where we look at continuous variable quantum key distributions on photonic chip. It's a very simple chip. Nowadays, if we look back, this is about 5 years ago, that chip can even be smaller, much smaller. Because, we went on to integrated photonics. I'll skip the details. And then we look at also at a protocol called MDI-QKD and implement it at the chip level. Now, the idea of implementing a lot of this on the chip level is that because chips are a lot smaller than bulk optics, you can actually implement some of these chips within a classical computer. And then you can do your usual QKD. In some sense, it's like steganography, where you hide the information. In some sense, you are using quantum, but yet you don't want to reveal that you are using quantum. And of course, so that is the premise. I'll skip those. And in fact, you can do a lot by embedding some of this chip within our handphone. And embedding it within the handphone is a nice feature that you can actually let little kids play with them, even though they are pretty inefficient, and one day they will get the excitement of doing quantum physics. So after all, it's only a tiny chip. I can embed it as one more component within a handphone. Now, the idea, of course, is, but this does not lead us to quantum computer. So we have been looking at various possibilities to produce an optical quantum computer. In other words, to reduce the bulk optics onto chips. Right now, I would say that we're not so successful. So even for niche computing, we're not there yet. But we did produce a so-called Malayan. Malayan is a creature that should not exist. Creature called Malayan Photonic Quantum Computer is really an optical computer. It's not a quantum computer. We do quantum computing with a lot of post-selection. And so that, as we know from KLM scheme, that drastically reduces efficiency. But let's look at some of the existing platform for computing. So typically, let's say we take the superconducting qubit. The chip is really tiny, doesn't occupy much space, but the fridge is really huge. And you need a huge fridge because you want to lower the temperature, and also you want to enclose the whole thing within low pressure. And the other platform, of course, is ion trap. Ion traps need temperature control as well, including addressing and precision control. So we apply this Malayan photonic chips that we have earlier on to some proof of principle financial application. And this is the chip. The chip is roughly a centimeter by half a centimeter. And we could see that we have some form of amplitude amplification within the chip. And that's the chip there. And the results have been published in this paper, if you are interested. We have cheated a little bit. We have traded the efficiency of a Hilbert space for unary-based photonic computing, in the sense that each mode represents one unit. Like if you start off with 0001, that's the first mode, and 0010 is the second one. So a photon goes into the second mode. And so it's not efficient. In some sense, if you have an exponential increase in resource in the number of qubits, then this encoding system is certainly not efficient. But we make use of some generative adversarial machine learning to counteract some of the disadvantages. Anyway, it's a proof of principle, and we showed that we could produce pretty good results that predicts some fictitious Monte Carlo simulations of option trading. So that was a chip that's been used. We used a series of Mach Zehnder together with beam splitters, and there's the quantum amplification part, and there is also a payoff calculation. And in terms of unitary and binary, there are certain aspects. Representation-wise, we know that the binary is always better. Chip architecture, binary is full connectivity, but the chip architecture for unary, that means encoding with single mode, is perhaps very simple, but also there are disadvantages. There's some caveat to it. Amplitude estimation, we don't have phase estimation, but over the binary part, we have phase estimation. KL divergence to a single qubit error actually is one order of magnitude lower in some sense, but that's also with certain caveats. So there are advantages and disadvantages. The chip itself can be used a lot for what's called boson sampling, and boson sampling sometimes creates the core of some computing, and in particular, we have used it to predict the molecular vibronic spectrum using squeeze states. So this time around, we need squeeze light source, and we plug it into the chip, compute the so-called permanence, but for continuous variable, so it's at Hafnian, and we show that the Hafnian is somewhat related to the probability of, the energy levels. Yeah. So, and then on Yasser Omer has a paper published some time ago where he looked at the quantum dynamics energetic advantage in a charge-based classical full adder. And then he looked at his full adder, some of the base cost and fidelity, and the cryogenic cooling that's required. We have for some time also been looking at Toffoli gate, just like he has done for the full adder with fracking gate. And the whole point is that if you look at programmable silicon photonic chip as a platform for Toffoli gate, classical gates, it certainly seems to do a lot better than simply because it's performed or operated at room temperature. This is going to the details. I'll skip it. So some good results. So let me switch gear a little bit. And there's a warning that the following video might contain material that may be harmful or traumatizing for some of the audience. And this is research that I did many, many moons ago, some 20 years ago, maybe 25 by now, where we look at where we induce colorectal colon cancer in rats. And then we detect the colon cancer with laser by shining laser lights onto the tumor, and then looking at the reflection light. It's sometimes in literature called laser-induced autofluorescence, LIAF. And so that's the tumor cells. And this is the size of the tumor. I have a sister-in-law who is now suffering from that. And she just got her tumor removed, but certainly it can grow to a substantial size. And so but this is induced. It's not God-created tumor. And you can also look at it from confocal microscopy, that they differ, and you study the characteristics. So the idea is that for the model, we look at rat, and then we induce errors. There were 25 rats used. At that time, there was not so much strict control over the bioethics. Now, if we want 25 rats, we will have to argue until the cows go home. And we inject it with exoxymetane, AOM, not the AOM that we know in optics. And this causes cancer. It's a cancer-inducing agent. And so you saw the cancer grows up. And then we shine light and we look at the reflectance, reflected light. And then you can take ratio of the light. And that ratio actually tells you, certain peaks tells you about the existence or non-existence of tumor cells. So some tumor cells may be benign, others may be malignant. And by looking at the peaks, you can sort of tell, but not so accurately. So what we did at that time was that we look at the same data, the whole data, but with artificial neural network. So that's done nearly 20 years ago with very bare minimum artificial neural network on I think MATLAB. And we look at the results to indicate whether or not the sample is tumor or non-tumor. And non-tumor, of course, the result must be, if it's a non-tumor cell, you want the result to be non-tumor. And in fact, as you can see from the sampling above, after a lot of training, the sensitivity and specificity is actually very high. It's something like 99%. But it looks like good mathematical result, but later on, we find that there was a better way of doing things by looking at the stools. And by looking at the stools, actually, you can characterize things much better. So why do I look at this history? The reason is because I went back, after so many years, to neural network again, but now on the photonic chip. And it has been shown by many people that photonic chips actually offers a way to do optical neural network. And the way to do it is that you implement, instead of implementing weights on the input states, you actually implement either a very big unitary or some modules of unitary circuits. And unitary circuits are built essentially from many, many Mach Zehnder. So each one of these represents a Mach Zehnder interferometer. The X with a slash across, that is just a beam splitter. But two beam splitter with some phase shifter, that represents unitary circuits. So by then you can decompose the unitary circuits. I'll skip that. And so you can actually do a lot of this quantum optical neural network on chip. Essentially, instead of having weights in the classical neural network, you replace them by unitary, whose angle has to be tuned. And the angles are nothing more than the phase shifters and the beam splitters. And a lot of work has been done to show that artificial neural network using complex numbers are much better. And so I'll skip those. We have shown that you could do it. And then recently, of course, we have also looked at how to do neural network regression analysis on the photonic chips with on predicting the entropy, enthalpy. So we take it from some known database and we try to predict the molecular properties. So this is a regression analysis that's done. And the results are pretty good. The experimental result on the horizontal and the theoretical results on the vertical. Do I have a pointer? But I can point you with this. Right, this one. And typically, you find that the results are all correlated in some sense. Oh, thanks. Yeah. I don't think I need it. So this is going to the nitty-gritty. And then there were people who look at complex network, as I said earlier on. And we implement an optical neural chip on complex value neural network, which is natural because at the end of the day, you know that your unitary gates are all made up of weights, and the weights are complex numbers in general. And the results is quite nice because it could predict. So these are data based on some artificial demarcation, and the complex model could predict better, but the experiment was even nicer. And then we have also done experiments with, so I'll skip this, with diffractive neural network. I'll not talk too much about it. This is trying to reduce the space that's required on the chip for doing neural network. And good results were obtained, but these are experimental results, so in principle. And the chip can be used for high-dimensional subspace teleportation and using what's called quantum encoder. So we build a quantum autoencoder within the chip, and then the quantum autoencoder essentially reduces the dimension of the input to a smaller dimension. And then because it is a smaller dimension, we could do good teleportation, and then we do the reverse decoding. And it turns out the results were quite nice. And so that was the chip, another chip that was being used. For random states, the fidelity were pretty high, not perfect, but more than 0.8 or even 0.9. So these are randomly generated qubits. So that's the size of the chip. This is a big one, but nowadays we can also make it even smaller. I'll skip all these details. So I'm saying that a lot of this chip-based quantum computing could be used for classical implementation of bulk optics. And in the process, we could actually even implement it within the industry because they are cheap. Well, they are not cheap, but experimental chips are not cheap, but the bulk mass production will be cheap. And the other thing about it is that you can actually make it with light. The laser beam, even the laser beam can be on chip, and so are the detectors. Some detectors can be on chip. And at the end of the day, what happens is that you have a very good low-powered device that can perform. So if you need to implement quick neural network, the training stage is done outside. But once you have done the training, you do bulk fabrication of the chip. Oh, I think I'm running out. Et voilà, merci beaucoup.
Perfect timing. Perfect timing, thank you, Kwek. Any questions from the audience? Yes, yeah.
I have a question on your optical neural networks. So on the slide somewhere, it was written that you need optical nonlinearities between your layers of unitaries, right? So how do you implement these on your chips?
With difficulty.
With what?
With difficulty.
Okay.
Say it's not easy. And the reason, of course, is, but there are ways to go around it. Lithium niobate has been tested, and we are very keen on that. The other one is silicon nitrate. Now, silicon nitrate is doesn't provide a lot of nonlinearity, but I think there is a group in France that has already used it to do some sort of deterministic quantum computing. Yeah. Now, without it, of course, you only have optical quantum computing. No, optical computing, sorry. Not even quantum.
You? Question over there?
Yes? There's a big room to run for giving away the mic. Maybe you can shout.
Thanks for the presentation. Just for general culture, so when you have this weight in this neural network that can be either real or complex, and so putting complex weight, is it exactly doing quantum machine learning, or is it just a different thing?
No, it's still classical machine learning with complex numbers.
Okay, okay.
So typical weights that's used in neural network are real numbers. But it was shown by some people that complex number provides an advantage, something like 10 years ago only, and one of them is a Turing Award winner, I think.
Okay. And so having because you have in some sense interference effect because of complex
yes,
number, but
naturally
this is not
provides that complex numbers.
Okay.
Interference, yeah.
Thank you.
Thank you. One question over there.
Thanks. Just a question about the energy cost for some of these special purpose photonic processing tasks. So like, for example, you looked at the these molecular frequencies. You got this using kind of Gaussian boson sampling approach. So what is, in terms of like the energetics for that, I mean, what would be the cost for that? I mean, you have to keep detectors cold. Do you have an estimate for how expensive it'll be to run that kind of thing?
Overall, I'm very interested to look at the energetics of these silicon chips. Personally, I must admit I've not done a lot, but in the case of the Gaussian boson sampling with the squeeze state, there's a lot of energetics that we ignore. We need to produce a squeeze state, and that's not cheap generally. I think I've hid it under the rug, but nevertheless, we should pull it out and compare, and it will be very interesting. Yeah.
Thank you. One last question. It was the same question. So no more questions. Then we actually have a coffee break now. And let's thank Kwek again for his talk. Thank you very much.